All right. Thank you very much, everyone, for being here. Happy New Year to everyone. For those of you who do not know me, my name is Lucas Burkhalter, and I'm with kind of a threefold identity here. So first of all, I'm the CTO of the Munich Quantum Software Company, a startup that we founded really just about a year ago. Was spun out of the work that we did at the Technical University of Munich, where I'm still a postdoc at the Chair for Design Automation of Robert Wille. And all of this is happening in the bigger context of the Munich Quantum Valley Initiative in Bavaria, which is one of the biggest initiatives in Germany, probably even in Europe, that focuses on quantum computing. For those of you that are not that familiar with the Munich Quantum Valley, I'll provide you a brief overview of what's going on there. And it's a collection of different institutions located around Munich in Germany whose goal is to develop and operate competitive quantum computers. And that in cooperation with a strong industry that we have in the surroundings of Munich and with startups like ourselves, but also other startups like hardware startups close to Munich to make quantum computing available for a broad range of applications. That's the very broad mission statement. All of this started just above 4 years ago. So we've been hammering on this for quite a while now. And the structure roughly looks like the following. It's structured from bottom to top, from hardware to applications in different consortia. And all of them have different responsibilities, from actually developing hardware, actually working on applications at the very top, and a huge layer of software as a glue in between, split among different consortia. The work that we've been doing, and when I say we here, I really mean our group at TUM, the group at the Leibniz Supercomputing Center, and Martin Schulz's group at TUM. We are K5, and we're responsible for the software stack efforts in all of this. So we're the ones trying to build the glue between the people developing applications and the people actually building the machines. The current setup in Munich roughly looks like the following. There are multiple different computers available in the Leibniz Supercomputing Center. First of all, on the right-hand side, you see a couple of IQM machines, so superconducting machines. Started off with a 5-qubit machine very early on, then moved to a 20-qubit machine. Since last year, there's a 54-qubit machine available from IQM, and we're looking for a 150-qubit system end of this year. So that's the superconducting side. But the cool thing about Munich is we don't only have one modality, we have multiple. The other ones being ion traps with a system from AQT that currently has 20 qubits, and neutral atoms developed by Planck, a Munich-based startup for neutral atom systems that plan to deliver a 1,000-qubit chip over the course of the next months and year. We're also looking for a photonic system in there, so we're also planning to incorporate these kind of characteristics into the software stack that we are developing. That's the overall situation in Munich. So for the big picture of why software stack, why would we need this? The situation is as follows. We have domain experts that want to do something useful with a quantum computer, that have tough problems to solve. We have quantum devices on the other hand, multiple different modalities, different maturity, and somehow we have to connect the two to one another. And what happens frequently at the moment is kind of this chaos mixture of point-to-point connections of some expert works on some machine through some software, but when they move to a different machine, they move to different software, which is totally intractable for the future. What we actually want, or what we desire, is a common software stack that brings together different applications and unifies different devices. So from both sides, we have this kind of combination effect to a common software stack that we can hopefully agree on. And this is also kind of the vision of this openQSE initiative here, to bring people together and avoid reinventing the wheel over and over again. And there are some key requirements that we had in Munich, but I think they also hold for basic quantum software stacks in general. And pardon me, the slide is a bit text heavy, but I think it's important to get these messages and key requirements across. And I think they align very well with the discussions of the past couple of weeks here. So first requirement is we need to support different modalities. The stack cannot only be focused on one modality because it's just not clear yet which modality is eventually going to prevail if it's even one, or if there's a need for multiple different ones, we need to be prepared for that. So there need to be different modalities that are supported. On the other side of the spectrum, we need to support many different programming models and abstractions. So the quantum community still heavily uses Python, for example, which is not particularly HPC focused or tailored, let's put it like that. And there are many different quantum frameworks out there that people are using. It's not like we have one SDK that everyone uses and agrees on. We have multiple. So definitely also important to have multiple different ways of accessing the systems available. Then I mentioned HPC already, and this is probably the context that we all share to some degree, is we want to integrate these devices into existing HPC centers as accelerators. A quantum computer on its own is probably not worth as much. It embeds into larger problems. It solves sub-problems that are hard to solve, but it's definitely not a complete replacement for HPC, nor can it work without it. So we need to integrate somehow into the existing infrastructure. For that, we want to be very efficient about the resources that we use. So we shouldn't let the quantum computer idle for too long, but on the other hand, we also shouldn't let the HPC system idle for too long, because that gets expensive pretty quickly as well. Obviously, it should be easy to maintain and to manage. There should be monitoring, there should be debugging capabilities. You need some kind of portal to access all the different statistics. And last but not least, it should be available. That was a requirement for us in Munich. It should be available for internal people, but also for external people. And people should be able to take the software that we are building and install it in their hosting entity and in their site and configure it for their demands. That was the thing that we set out for. And the following is the architecture that resulted out of this. I'll try to build this interactively, and then I'll show you the paper version of the figure, and hopefully they match. So we have this big blob of a software stack that connects the end users and the devices. And the first thing we definitely need is we need an interface for the front end, for the different programming models, for people to access the stack. And this could be multiple different frameworks. This could be Qiskit, Penny-Lane, NVIDIA, AWS Bracket. This could be some of our Munich solutions out there. And this list is definitely not exhaustive. So there are dozens of additional tools. And sorry if your logo isn't on there. There's only limited space on these slides. But we need a common interface for this so that we don't implement 10 different paths within the software stack that go through the whole software stack. And similarly, on the other side of the spectrum, we need a backend interface. We need something that abstracts away the individual characteristics of the devices, whether this is now an IQM machine, a Planck machine, an AQT machine, whether it is an emulator by Eviden, or again, one of our own solutions. We need a common interface, and this is actually also what I will spend most time of this talk about because it's the most ripe software solution that came out of this effort. But key component there. Then I mentioned HPC integration. So resource management and scheduling is extremely important, naturally. Two things to mention here are, on the one hand, obviously Slurm, because it's one of the most common scheduling systems on the HPC side, and how to tie into this. And on the other side, if I have 10 different quantum computers available, I also need to somehow predict where should I run, when should I run on a device, and given a particular application, which quantum computer out of my whole portfolio is actually the most reasonable one to use. We've been building some research in that regard. This all runs under the name MQT Predictor. So MQT is the Munich Quantum Toolkit, collection of software tools that we've been building over the last years. And the aim there is really to train models that could predict things like runtime of circuits, where you should run them, what's the best option for scheduling. And it even goes a bit further and ties into the last box that I'm about to unveil. It ties into the compiler infrastructure, namely, how should you compile your circuit? How should you compile a particular application for a chosen device? And models and training can also help here, and also kind of co-influence scheduling. So compiler infrastructure and scheduling, they are really tied together. What you see in that picture, you don't have to read that in detail, is basically an MLR-based compiler infrastructure that takes in the various front ends, lowers the dialects down until the very bottom where you see QAR as a common exchange format. And this is actually what we would expect to send through the backend interface to all the backends then. While not everyone supports QAR, we also have a path that exports to openQSE. So if that is something that people are more comfortable with, then you can go with that. And there's also ways to add proprietary formats for the backend interface. But we should, as a community, aim towards less formats and more standards, and not create more formats as we go along. So also kind of a key priority. That's the interactive building of the diagram. The paper figure looks like this. So you can find the preprint on Archive. This will be presented at HPC Asia in, I think it is 3 weeks from now. So if you're in Osaka, then please come along and watch the presentation of that as well and join the discussion. If you would want a more complicated version of that figure, because this is still just gray boxes with text, that's the full architecture diagram at the moment. So this is basically every single gray box represented or blown up with the individual components in there. And what you can really see, and I hope you can see my laser pointer, is you can see a front end from either Python stuff or C++ stuff that goes through a common interface, either through remote access or HPC access, goes into this scheduling and compiler infrastructure middle end, and then it goes to the back end, where there's again one common interface. And this is actually the interface that I want to spend most time now talking about. So if we look at the big picture again, the one question that we started out with was, how do we actually connect the software developers, the people developing the software stack, or that are supposed to develop the software stack, with the actual hardware and the hardware providers? And what we did is pretty similar to the community round here. We did what we call technical exchange meetings. So we got together a huge bunch of people from the Munich area and had them talk, essentially. So we wanted to connect. We had everyone in the room. Every 3-4 months, we would have a meeting. We had different working groups. And this all sounds so nice and so productive. I want to recollect how this went roughly. So we as computer scientists approached the people, okay, give us all your requirements, give us all your tools, we'll collect them. This was a collection of Post-its of all the tools that were around in the Munich area that either have been developed or that will be developed, and kind of a couple of constraints. As computer scientists, we then rearranged this roughly to a stack-like figure, top to bottom, applications on top, hardware on the bottom, and categorized these items. And then we even drew beautiful flowcharts. And then we approached the experimentalists and asked them, hey, is this something you could work with? Did we understand you correctly? And they were saying, no, not at all. We can't work with that. Okay. Then we asked them, can you provide us with information how you would like it? And that roughly looked like this. So this is a big mind map. You don't have to understand the details. It's just, it contains a lot of information about the experimentalists and what they cared about in their machine. And we looked at this and said, like, yeah, this is not something that we can work with. This is way too detailed. This is way too low level. We can't build a software stack on top of this. So after 3-4 meetings, so basically in a year of meetings, we were basically nowhere, or we felt like we were nowhere. So it was like 2 different perspectives, completely clashing with each other, people with different backgrounds. But we didn't stop there. We pushed on and we tried to align the languages between the different groups. And actually that was quite successful. So after a year of struggling, what came out of this is really the first kind of substantial piece of the Munich Quantum software stack. And this is called QDMI. So many of you in here will have already heard this. This is the Quantum Device Management Interface. And it is really supposed to be the back-end interface of the software stack. So, sorry for that. If we look at this big picture, you have a circuit on the left-hand side, very abstract, and 3 platforms on the right-hand side. And you want to run that circuit. And even in that simple picture, there are lots of questions to be answered. First of all, you do some device agnostic compilation, and at some point you want to choose a device. And after you've chosen a device, you want to do some device specific compilation, and then you want to submit the circuit. But for that, you need to know which devices are available, which of them are even online. You need to certainly know the constraints and the characteristics of the device in order to compile well for it. If you don't know what you should be compiling for, then that second compilation step will be pretty damn hard. And you need to know how to actually submit jobs and get back results from the device. And on top of that, it would be good to have some kind of calibration information so you know how the device behaves on a given time of the day. So lots of questions to be answered. And most SDKs for quantum allow you to query that information or allow you to do this some way or another. But we didn't want to have 3 different solutions for 3 different platforms. We wanted to have one solution. And that one solution is QDMI as an interface. And it allows you to submit jobs and get back results in a unified fashion. This is the pretty standard. You submit a job, you get back results. In addition to that, it also allows you to query information from the devices and feed that into libraries that inform your compiler. So this is the thing that sets it apart from basically just Slurm resource management, submitting jobs and getting back results. It also allows you to query information about the devices that you need in the software stack in order to do compilation for these devices. And I want to dive a little bit deeper into the architecture of QDMI and want to show you how it looks like, how it feels like. And for that, we have to see QDMI as follows. So on top, again, of the clients or the users and the software stack. On the bottom, we have the devices. In between those, there's something that we like to call the driver because it mediates the connection between different clients and the devices. And then we have 3 entities of QDMI or 3 parts of QDMI. The first part being the session management interface. Think about it as resource allocation. You want to have user control. You want to have access control. You want to specify some kind of authentication information. So the boring stuff, so to say. Roughly looks like the following screenshot. You don't have to read all of that in detail. The general workflow is pretty simple. You allocate a session, you set some parameters like authentication parameters, you initialize the session, then you can use that session with the remaining 2 interfaces, and if you don't need it anymore, you free it. Pretty standard stuff. The next part is the query interface, the part that lets you query information about the device. And for that, there are 3 main entities. There's the device itself, meaning really the physical quantum computer. There's the individual sites, or you could call them qubits. Not all, doesn't make sense for all modalities to call everything a qubit. For example, for neutral atoms, you have individual sites, which might have a qubit or not. And you could ask them for properties, things like T1 times, T2 times. And then you have operations that you can do on that device. These need not be gates, could also be something like, for example, shuttling on neutral atom platforms. And you need to query some information about these operations. That's the query part. It's 3 functions, one for querying device properties, one for querying site properties, one for querying operation properties. All of these functions, so QDMI is a C-based interface for compatibility with various frameworks. So with the main intent that you can implement it in any language and use it from any language. That's what C gets you. And you can control the property that you want to query by an enumeration value. There's a huge, I'm not going to show you the list of enumeration values. It's quite long by now, but these are the things you can query. And then the last part in all of this is essentially the job interface. And this is your standard job cycle. This is basically you create a job, you set some parameters like the program, the format, the number of shots. You submit the program, you check its status, you wait until it's done, you get results, you free the job once you no longer need it. So pretty standard job cycle, but standardized as a C interface that you can build on. QDMI itself comes with full API documentation, so we try to document the interface as rigorously as possible. So it is merely an interface by heart. So API documentation is all you get in the beginning. But we go 1 step further or 2 steps further. We provide reference implementations for devices. So for the bottommost entity, we provide a reference driver, and we provide very basic clients, like a tool that uses QDMI devices. So you can get some inspiration on how this looks like and feels like. And there's also a development guide if you want to contribute, how to set this up, how to contribute, which tools to set up, and what we expect from you. In order to give you a little bit more impression on how it looks like actually to use QDMI, I want to show you something from the extension we did for neutral atoms. So this is done by a colleague of mine, Yannick Stade at TUM. And he made this beautiful slide of where you start basically with a Python console, so the thing that most people in quantum are familiar with. And you import from a library, you say, hey, give me the first device that you have available, and then you can query the device for its name. This is a device property. And then you can query one of its sites, maybe the 24th one, for its X coordinates and Y coordinates. These are important for neutral atoms because the atoms are really arranged in a grid, and the location is kind of important for compilation. So this is something that we added on top of the standard. Like there's just a site, this is a qubit, it has an index. And then you can query each operation, for example, for its name. And what you see here is also you see the standard kind of Qiskit notation of gate names, but then you also have some neutral atom specific operations that are definitely not gates. They are basically loading an atom, moving it around, and storing it somewhere. This is what the device reports. What happens under the hood is basically this connects to the driver that we have, and this loads from a QDMI device library. That device library basically implements, in this case, the query functions that I've shown you on the previous slides. So device properties, site properties, operation properties. And because implementing C functions can be a bit cumbersome, we took it one step further and basically provided a generator that can take a JSON file and generate a device implementation for you out of that JSON file. All of that is available currently in the MQT core project, but we plan to upstream this to the QDMI repository so that it is more centralized and that you get even more fleshed out examples right out in QDMI itself. So this is basically the QDMI part, the how to abstract away devices, different modalities, how to use that. Now the big question is, of course, how does that fit into the whole HPC QC infrastructure? And for that, I want to spend a couple of minutes to highlight some of the work that we did together with IQM, where what you see on the screen is basically your standard Slurm setup or HPC Slurm setup. You have a login node that you can you have remote access to. You have a Slurm controller, you have some classical nodes, a database, and that is it. And now the question is, how do you get quantum into there? And one way to do it, not saying it's the way to do it, but one way to do it is to basically add another node, a quantum worker node that has some classical compute that you could use for compilation, for example, but also for running the different jobs. And it has kind of, again, this threefold structure. So it has QDMI on the bottom. This can connect to either on-premise devices or cloud devices. Then you have some kind of compiler infrastructure. And then you have some computational primitives here, like for those of you who know Qiskit, the sampler and an estimator primitive that you can use from the algorithm side. So you have the front end part, you have a compiler infrastructure, middle end part, and you have QDMI on the bottom part. So you could consider this a mini software stack. And this all ties to some classical compute resources and hooks up to the standard Slurm setup. And how it would look like to actually run something on there is quickly demonstrated in the next couple of slides. So for those of you who are not familiar with QSCI or what that is, it is one of the prime use cases from quantum chemistry that is currently being explored for quantum advantage or quantum utility, or however you want to call it. It's basically for finding the ground state of a molecule. And what we wish to achieve at some point, and what we demonstrate also in this demonstrator project, is you want to import some function for running the algorithm. And the two things you want to do is you want to specify your problem. This is a very simple one of the H2 molecule, just for demonstration purposes. And you want to specify that you want to offload this to an HPC cluster and whether to use a simulator or a real device. And what you should get back is the result. This is basically how, hopefully in the future, some people will use quantum computers, at least in our view. Of course, in the background, a lot more has to happen there. So what happens in that run QCSI call? You construct your problem instance. That's the first part. This is very problem specific. So for a different kind of problem, you would construct a different thing here. Then you prepare some ansatz function. So this is using some variational quantum algorithm in the background to prepare the ansatz. There's tons of literature out there for how you could be doing this differently. This is just for demonstration purposes again. So you prepare an ansatz, then you sample from that ansatz circuit a couple of times to get your results, and then you do some post-processing. And basically, the first part can happen on a classical computer or a quantum computer, depending on how you prepare your ansatz. The second part happens on a quantum computer, and the last part typically happens on an HPC cluster for doing matrix diagonalization. And internally, this sample slurm looks roughly as follows. So these are the two components. That's what the user writes, and on the right-hand side, you see what happens on the quantum node. The high level, this is abstracted away a little bit, is you dump the program, you submit it with Slurm, and then after it's done, you get back the counts from the results. And on the quantum daemon, you load the circuit that was serialized, you initialize a backend, you compile for that backend, you run the circuit, and then this is an asynchronous call. You get the counts, send them back. As simple as that. So this is very just for demonstration purposes on how to imagine this all working out. And this has been pretty successfully run as a demonstrator over the last couple of months, and we plan to extend it in the future by multiple different things. This is actually the demonstration part of the MQSS, or this was the demonstration part. I'd like to take just the last couple of minutes here before we hit the half-hour mark to explain you what's next. So obviously we're not done yet. We've been doing it for a while, but there's a lot to do. And one of the key things there is really to stabilize what we have right now. To basically have good CI/CD practices established, to have testing established, to really make sure that what we have works, and that this is not just an academic project, but that this is a true software product that can be used in production. So this is definitely one of the key priorities, taking what we have and transforming it from something that is still very academically touched to something production ready. The second thing is then the kind of evolution part of it, making it better, faster, brighter, broader, applicable, developing new components in all of the software stack, integrating it with more devices, with more front ends, with more programming levels, programming abstractions, and to really get users on there. And the last part, which one shouldn't underestimate, is kind of the revolution part of it, is how to deal with fault tolerance. Like all that I said previously definitely holds for NISQ. It's not so clear if all that I said holds for fault tolerance. And it would be pretty damn bad to not think about this from the get-go and to keep this in mind that fault tolerant systems will come and that we will need to deal with them, and that they have, I don't know, different constraints, different characteristics, different needs for compilers. And we should design a system that basically takes all of these requirements and fits them to the current stack model without changing everything, without basically ripping apart the entire stack and building a new one. So this is also the third key priority for the next couple of years, to keep this in mind and to develop the stack forward. With that, I'd actually like to hand it over to the audience for questions right now, if there are any. So thanks for the attention so far.
Thanks, Lucas. Any questions out there? I have a few, so but I'll wait for others.
There seem to be questions. Just go.
Go ahead, Mike.
Hey, thanks for the talk. I was just wondering if you can characterize the sort of current, production readiness or not of these components. I mean, you mentioned it's sort of academic now and you're trying to get it into a more production ready, but like, where in that spectrum would you say you are today? Thanks.
Yeah. Let me go back to the overall picture here, and I think the right-hand part, so the part that I talked most about, QDMI, is actually pretty much production ready in the sense that this is being used by almost a dozen different players right now, not only around the Munich area, but around the European landscape to integrate their systems into the things we're building in Munich, but also not only in Munich, but more generally to find a common interface. So that interface is pretty much production ready, I'd say. It's also the repository is well maintained, it is documented, it is updated, it has proper development cycles. So that part I'm pretty damn happy with personally. The compiler part is changing substantially over the last couple of years. So I wouldn't say that that part is really, really production ready yet, at least not in the way that I would like to see it at some point. But this is more so a fact that also the community is frequently changing when it comes to compiler infrastructure. So the last 1 or 2 years have seen such a rise in MLR-based compiler efforts or MLR-inspired compiler efforts that just hasn't been there 2 or 3 years ago. So I'd expect some substantial changes there still, but we're aiming to get at least the interfaces, basically QDMI, and the other side of the interface stable as quickly as we can. So the changes in the compiler infrastructure actually do not make that much of a difference for both sides. And lastly, for the front end side, I think this is kind of in the middle between the two. Obviously, we have connectors for certain front ends. Those vary quite widely from hack together, made to work, to well supported, and we'd actually recommend this for people to use in production. So I think there the variety is pretty damn big. So maybe one could say that from right to left, it gets less and less production ready, but we're working our way forward. Does that help somehow? Or make sense?
That helps a lot. I have another question for later, but I'll get in the back of the line. Thanks.
Makes sense. Next, please.
Go ahead, Johannes.
Hey, sorry, can you hear me? New
Yes.
laptop. All right. First of all, thank you. I really like your talk. I'm gonna be, I think, one activity that is sort of ongoing here is also a high-level kind of requirements and use case study. And I think this information that you're showing here allows us to at least be able to turn some of the hypotheticals into other people are doing this, therefore it must be good.
At least we've been trying for a couple of years, and this is what we came up with. I'd put it like that.
And the fact that you've been trying for a couple of years speaks to the fact that this is not easy, but also, there's benefit in doing things carefully. Which at least that's sort of how I want to correct me if I'm wrong. Maybe it's just, you're understaffed, and that's also something that we are all suffering from. But to my question, you shared a diagram earlier where you kind of contrasted the software engineer's view from the the domain scientist's view. Yeah, this one. And so I was wondering if you there's the social aspect of this, which never be understated and can't really be gotten rid of. But then there's an engineering aspect that I think is sort of possibly solvable. And what I mean with that is there are languages like Julia that try to avoid the sort of front end, back end, the problem with languages, in my experience in this space, has been most languages, you have to be a back-end engineer to work on the back end, and sometimes the front-end user will come up with use cases that the backend engineers haven't considered. A really common example that I've encountered a lot is in AI, right? Like if nobody's implemented the loss function that you need in PyTorch, then you're kind of in trouble. So there's actually an interesting PyTorch post about this where they said like, well, we ain't gonna use Julia, but what we'll be building is very similar to Julia in the sense that they're thinking about JIT, allowing you to sort of JIT through the LLVM stack and expose some of the internal guts of the backend to the front-end user. And I wanted to see if there's any activities like that on your end. Or even if you're going to say we are going to build a Julia thing, that would be even better.
Yeah, so multiple different ideas that are floating in my head regarding this. So there are definitely efforts in that direction from multiple different fronts, not only from us. Also, when you look at the compiler infrastructure field at the moment, you see people actually building compiler infrastructure for quantum in Julia. QEra's Kirin is exactly that, basically.
Yeah.
Takes the idea of MLIR plus XDSL, which tries to do MLIR in Python, and mixes it with Julia and builds a compiler framework out of this. Definitely a way forward. You see Quantinuum doing something very similar in that regard, building their own framework that is, again, MLIR inspired, but not directly building on MLIR to facilitate some more structure that you would need for quantum. So I think there are multiple initiatives there. And also to your point of exposing this to the user, I think this is very important at this point in the development of the software stack, that you don't abstract away too much. So the example I showed for running QSCI is nice for the people that do not care, but this cannot be the only abstraction that we provide, because if someone that is really interested in the technical details and that is a researcher trying to work on algorithms, they need deeper access. They need access,
right,
maybe even down to the pulse level. Maybe. I'm still very hesitant to actually recommend that, but at least they need control over the compiler and the abstraction level that the compiler works on. So it's definitely important for us to make this accessible to people. So in my priority list, it's the easy access first, so like that people can just run things so that they can see, hey, okay, this works, you can do something useful with it, so kind of the hero runs, but then immediately afterwards build the customization, build the lower level access for people. That would be my priority list here.
Right.
Maybe one last comment on the first aspect, because you mentioned social versus engineering part of it, and I couldn't agree more. Like, definitely this also has a huge social component, and it took us the better part of a year to actually sit at the same table and be willing to talk to one another, to understand the different party, and to kind of find the same terminology so that we could all agree on what we think is compilation or transpilation or whatever you want to call it. So one shouldn't underestimate that effort, that really coming together regularly and being open-minded to change the perspective that one has in his or her own head is incredibly important.
Right. I agree entirely. And that will also allow you to then leverage the community. You mentioned priority list. These are always longer than we have time for. So maybe there's also opportunities here to let the community work on exposing things that they need.
Yes, very, very much so. Like, I see this in my personal work. So where I come from, or where we come from, is actually not the quantum domain. It's classical design automation. So basically chips and integrated circuits design. We started out there, and this was our community, and we basically brought quantum to that community. Then we more and more switched to the quantum community and brought computer science expertise or design automation expertise to the quantum people. And over the last couple of years, the HPC QC bubble became bigger and bigger and bigger. So we now try to combine all three kind of expertises. So the knowledge from the quantum software community, our background in circuits and system design, with HPC expertise. So we already have access to three different communities at least, which is really, really, really important. And we try to maintain this, although it is hard at times, because Every community publishes in a different way. Conferences are different. Deadlines overlap. So it's not easy, but I can only recommend for us as a community to spread our wings out or our, I don't know, our threads out and try to contribute as much as possible to different communities.
Couldn't agree more. I yield the rest of my time though.
Amir, I think you're next.
Yeah, I have a couple. We'll stick with one question that's maybe nitty detail. Like if you go back to the very first slide where you show the breakdown of the front end, the programming paradigms, front end. Yeah,
this one.
Yeah. So it seems to me that, okay, I just want to try to understand, like you support Qiskit, Penny Q2Q. Do you write a back end specifically for each one of those such that that back end interfaces? I'm gonna put back end between quotes, but like a back end for that platform to interface with the front end of the MQSS software stack?
Yeah, that part is still pretty hacky, to be honest. It varies very much between the different front ends in how satisfied I'm personally with the solution. So for Qiskit, the way it works is basically we take QDMI at the very bottom and we expose it. First of all, it's a C interface. First of all, we expose it to C++. We expose that to Python. And then on top of the Python bindings, we wrap a Qiskit target implementation. So a Qiskit target or a Qiskit backend is nothing else than it allows you to query information and it allows you to submit jobs to the backend. So we provide all of that on top of QDMI. So this is really more or less the fully fledged access model. You can hide the compiler infrastructure in between there in the middle, and then you can use any QDMI device just as you would use a Qiskit device. That's the kind of level of abstraction or ease of use that we would like to aim for the other kind of frameworks as well. But it's not as easy for all of the frameworks. So first of all, it's much tougher for the C++ based frameworks because plugins for compiled languages are just tougher to write and distribute. But there's also just so much time to work on all of this. I think the second best supported platform is still PennyLane, because it gives you nice ways of playing with NISQ algorithms and variational algorithms. So the PennyLane device implementation for the MQSS is also pretty well supported, I'd say. And if you go to the paper, you'll also find, so paper being this one here, you'll also find links to the respective interface documentations on how this currently looks like. This is on my 2026 roadmap to streamline this a little bit more and to flesh out this, what's being written here as the MQSS client interface, to flesh that out a little bit more so that it's one interface that you then build on. Does that roughly answer the question?
Yeah, I have another one, but related to that, but I'll leave it to after. Thanks. I think I'll go with the next one is
Alex.
Hey, Lucas.
Hey.
Thank you for the talk. I enjoyed it quite a bit. I do have a question about maybe this slide and one of them on the motivation for including compiler in the stack.
Mm-hmm.
It's by far the most complicated part of the system, and it's by far the most varied, particularly if you try to compile across different platforms. Is it because the quantum computers you're dealing with don't come with a compiler, or is it because you believe you can implement a better compiler than AQM or AQT? Or what's the motivation?
So multiple different points. So on the one hand, that's the arrogance speaking out of me. Yes, I'd say we can at times build better compilers than some of the vendors. For the sole reason that is totally understandable in my opinion is that the purpose of, or their goal is to build hardware, and they're pretty damn good at building hardware. I could never construct such a thing. But typically the people that are building hardware are not the same people that are good at building compilers. So there's a certain overlap definitely, and some of those companies have great compiler engineers, but there is room for improvement for many of those. And also there are still many compilers being written in pure Python, which are like, they're too slow. And I'm not quite sure if it should be the responsibility of the hardware providers to develop better compilers, or that leads to the second point, if we could abstract that away from the hardware providers and provide one centralized place where there is a compiler infrastructure with different plugins for different modalities, where the community could contribute compiler passes. This could still include the hardware provider, so we don't want to forbid the hardware provider to develop a compiler, but we'd like to make it a bit of a broader audience for actually contributing stuff to this effort. And I think maybe it's not MLR as a framework itself, but the notion of MLR, that you have different dialects that you can translate between. You have passes that run on these dialects, and you can basically within the program mix different dialects as well. I think that resonates quite well with this vision of having this interchangeability between different frameworks in that compiler framework. So like you have the compiler infrastructure and it uses different dialects, and some compilers work on that dialect, some work on that, but you still have one infrastructure that runs the whole compilation. And I think there's a lot of value in building such a thing. So instead of having every single hardware vendor implement a full stack quantum compiler, or just copycat the existing solution that there is in some other SDK, for example, a neutral atom provider copying the superconducting compiler solution just because it's available and it may be open source, that is not a way to write a performant compiler for the platform. So that's mostly the two strings of the answer. So first of all, I think we can write better compilers, and I think we should have a broader audience that can contribute compiler passes to that infrastructure.
Thank you. That helps. The reason I asked is because it really drives what you expose on the back end. You talked about sites, you talked about connectivity, you talk about things that normally as a software stack vendor you shouldn't really care about. But as a result, you require the backend to expose all the nuts and bolts, all the guts of its implementation in order to work with it, as opposed to moving the abstraction layer a bit farther away from the device and only dealing with the quantum concepts, where I could absolutely see a lot of community effort going into developing quantum-specific compiler passes. But developing compiler passes that are specific to neutrals versus photonics, that seems maybe, well, for me, it would be too big of a pie to show.
I definitely see your point, and I couldn't agree more, which is also why this kind of red line between what a hardware provider offers and what the software stack kind of produces or is expected to produce, in my view, is not a fixed line that is set in stone. This can be very much shifted. So like it's totally viable for a hardware provider to say, you don't get access to these low-level details. You can send us any openQSE circuit that you want, and we deal with the rest, and you don't get access to more because IP, because we think we're the best. I don't know, you choose your favorite reason. This is totally valid in my opinion. The thing is just, we want to be able to get the information. So if the hardware provider wants to give the information or is willing to give the information, then we want to expose it to the compiler stack, because people are building neutral atom compilers. They are building passes for neutral atom compilation. And the more we standardize around the language, the programming formats to use and kind of the exchange format, the more we can all benefit from these developments that happen mostly in academia at the moment, behind closed doors at companies. But if it were easier for the academic side to contribute to a common pool of passes, it would definitely be a win for everyone.
Thank you. I yield.
Neil, I think you're next. You're muted.
Thank you. Thanks for that, Lucas. That was a great presentation. We chatted at, I think, in Albuquerque at IEEE Quantum about a reference implementation for QDMI, and you had mentioned that it was like kind of going to be there. And in this talk, you kind of talked about that like JSON kind of builder for the QDMI stuff. Is that part of what you were kind of in terms of your reference implementation you were mentioning then?
Yes and no. So there's more. So on the one hand, yes, this is part of it. So this is part of the reference infrastructure that we've been building. So what's currently contained in MQT core here is really, it's what I just mentioned earlier. On top of the C interface, it's a C++ interface, it's Python bindings, it's Qiskit bindings, and you can really use all of that with your QDMI device if you have it. So this is basically from QDMI upwards, or the pictures that I've just showed from QDMI leftwards towards applications. And the other side of the interface has also improved quite significantly. So just before Christmas, we pushed a new update for QDMI that has a much better device template. So if you want to implement your own device, you can go to the QDMI repository, you need to clone it, and then you can configure it with a template. You give it a name, you give it a prefix, and it spits out a complete boilerplate project, including distribution mechanisms. So including the mechanisms for distributing this as a Python package that people could install for getting the shared library that you're developing and all of that kind of stuff. So we're slowly moving towards more, towards not just an interface, but actually an ecosystem around it. So yes, I would say so. There's a lot of work has happened on top of QDMI, but also below QDMI. And more will happen in the next couple of months. So we used the end of the last year to really reflect on the things that worked well and the things that didn't work too well. And we try to implement the changes based on that over the next couple of months. I don't have the perfect time frame here, probably first quarter of the year, roughly. So kind of the next iteration should be ready. I don't know, if all of you are at ISC in Hamburg in June or so, there will definitely be something to talk about.
Fantastic.
But even before that, I suppose.
Cool. Look forward to it.
All right. Peter, I think, is next.
Yeah. Hey, everybody. Thanks for the talk. It's really impressive to see how far along you guys are. So I had a question about resource scheduling and allocation, in particular for these very hybrid jobs, let's say, where you need this constant back and forth interactions. So is that both quantum and classical hardware pre-allocated, or is it allocated on demand as the job continues and you have to switch between the different modalities?
Yeah, I think it's very hard to make a definitive answer here, because this is probably the thing that will change most over the next couple of months, or that also has changed quite a bit over the last couple of months and years. How to best schedule hybrid jobs is, I think, an open research question. Even there is some ongoing research in that regard, not only from us, but really from the community. And I think so far no one has really found the silver bullet and the one thing that worked for them. The thing that we did here in this project together with IQM is basically we said this quantum node has some classical resources that are powerful enough to run the optimization step of a variational quantum algorithm, for example, so to run the optimizer. So you would send the job there. This would be blocked for the duration. It would compile the circuit, preferably already in the parameterized form of the ansatz. Then it would run the circuit, feed back the parameters, do the optimization, and it would all happen in this kind of node here. And then you would feed back the result to the login node for the estimation task. I'm pretty sure this is not the most optimal way, resource usage-wise, because you do block off that node. Additionally, you first of all need to have such a setup that you have a dedicated quantum node that can basically handle this. But I could imagine that this is a good blueprint for how to move forward with this, that you have for a job, you have a certain number of nodes allocated for running the variational part, and the classical part stays allocated, probably, because for most of the platforms, for most of the modalities, jobs are fast. So especially for superconducting systems, something like 10,000 shots is fast. For ion traps, for neutral atoms, that might be a little bit different. So the timescales definitely vary, but I think that is fine. And then you kind of schedule around that. You mentioned switching to different modalities or to different computers in the job. And also, I think that is pretty much ongoing research. Whether that is actually a good thing to do or not, it definitely has the pro that you probably get better utilization because you can just switch to a quantum computer that is free. It definitely has the negative points that you need to compile again for that quantum computer. So it's no longer as easy to just say, hey, I have my variational ansatz, for example. I compile it once for my system in parametrized form, and then I just reinstantiate over and over again and send. For a different modality, I need to do different compilation, and that takes time and effort and resources and also needs to be scheduled again. So I think it gets pretty complicated pretty quickly there. So what I foresee, at least for the production future, for the foreseeable future, is actually that people will just do a very basic scheduling on that side. We'll just basically allocate one quantum computer, not switch between different quantum computers, but allocate a dedicated time slot there. I'd hope that there will be some improvements for the interface between classical and quantum parts of a hybrid job, so that the latency there is a little bit lower. But I think I'd rather strive for a solution that works first and then optimize than the other way around, to optimize like crazy beforehand, not ending up with a viable solution at any point. But that's just my 2 cents. Feel free to disagree.
Yeah, great. Thanks a lot, man.
So at point on time, we are out of time, but there are a few more questions. I'm okay staying longer if people are willing to stay. So
I'm also okay. I'm available. So please feel free to go ahead. Neil, I don't know if you still have raised your hand or if there's a new question from you.
Oh, sorry, I just didn't take it down.
And Peter too. So I think the next one is Johannes. Yeah.
Actually, I wanted to add a different observation to this diagram. In HPC, it's very tempting to start drawing boxes around things. And so I should have waited before you finished drinking your drink. And there's a hidden danger to that. We're seeing this with a lot of the classical HPC systems as well. I mean, this is one of the big lessons learned there. When you start to have a very tightly coupled mindset, you start to box out new kinds of applications that won't fit into these boxes. The example that I have worked a lot with is, what about plugging an HPC system into a real-time experiment? Well, unfortunately, we drew the boxes in such a way that the compute nodes can't see the internet, right? And like every box has a good reason. I'm not saying don't put boxes, but like especially, I agree with your point. There's optimization around utilization, but then there's also the idea that like if you box out your quantum accelerator too much, then you might not be able to slice and dice your jobs in a way that's not anticipated by the boxes. So please be aware of that.
Yeah, thanks for that. Great point. And it's also it's part of the reason why there is really an on-premise connection here and a cloud connection here in this box. I fully agree that it's still a box, but at least it foresees two different access paradigms from the get-go, that you might not have the quantum computer co-located with your HPC resources. You might have it in the cloud somewhere. Maybe you don't even have your HPC located in one location, but you have that distributed. I don't know. Think about an AWS cluster setup or something like that. And then also you have access to different
HPC. Your HPC is very toxic to quantum states. It's warm, it's electrically noisy, it's mechanically noisy.
Yeah, I mean there I'm probably not even the right person to talk to. I don't know if Martin is still in the call or if anyone from the LRZ side is still here. They had all the experiences with putting the quantum computer right next to the supercomputer at the LRZ. And there's even, if you go to the archive, it's called something like First Practical Experiences, something Munich. You'll find it if you look for it, and I can share it in the Slack channel later on, where they actually describe the practical challenges of hooking these systems up to the HPC. And these are as trivial as fitting the damn thing in the elevator and bringing it up and then mounting it. And then I mentioned in one of the key requirements that you need to be able to observe data and monitoring stuff. And two funny stories. One, they had lots of data, monitoring data, and then they looked at it and they tried to correlate it with the performance of the system. And there were some unusual spikes in bad performance that were pretty damn regular. And they changed over the course of the day. So it was every 10 minutes in the rush hour period, and then only every 20 minutes overnight. And it turns out that was the U-Bahn schedule in Munich that changed at a particular time of the day. And this was measurable. Second funny story, then I'll hand it off. I think, Martin, that might be you. You can also add something to that. But it was, I think it was the AQT system, but doesn't matter too much. Technician called, hey, what have you done to the system? Something drastically changed. And everyone was confused and no one knew what was happening. Turns out they moved a metal letter from one side of the room to the other side of the room. And that completely threw off the shielding of the device and the calibration. So yeah, this happens. This happens when you move out of the lab and into an HPC center. So be prepared that things are different. But Martin, maybe you want to add something to that.
Well, hi. So this is Laura Schultz. We're just sharing the same. Hi, everybody. Happy New Year. Yeah, to the point about the the HPC systems being toxic to the quantum systems and whatnot. I mean, I think that is true for maybe this point in history. Although we've already seen that the systems are actually a bit more robust than we maybe gave them credit for initially. I mean, we definitely do have some problems, and there are variances, but that's really part of the co-design, and that's really the purpose why LRZ created like the Quantum Integration Center, to really put an experimental space to force these systems together in the same environment, with the understanding that quantum systems were going to become eventually they're going to become more, I don't want to say mass market product, but for advanced computing, but they want to produce these systems, they want to get them into data centers, into HPC environments. So there is a reality. There's going to be large quantum systems that are going to have this instrument level designation or experiment level designation, and however that realizes itself. But we can, with the philosophy very early on, these systems are going to be in data centers, and we're going to be working with the companies on this path to harden them and to mature them into an environment where they would naturally be seated, and as accelerators to HPC, they would naturally be in HPC environments. So whether that's going to be on different floors, right next to each other, that was the whole idea of LRZ. And right now there's two quantum systems seated right in the HPC center, right next to cluster systems, and they're actually performing surprisingly well. So this is all open questions as we go on, but we kind of went with the premise that if these systems are going to be in the market and eventually useful for science and eventually in universities and all of this, that this is part of the evolutionary process that these systems have to take on.
Right. That's a good point.
Sven, you had something to add.
Yeah, I think Laura did it much better than me, obviously. She has all the experience here. I'm talking to a lot of the different companies in various forms and fashions, also because of potential procurement interests. What I see is a very strong shift over the last couple of years in the understanding of what a data center is, what you can and cannot do in a data center among the companies. I don't want to step on any toes here. I do see we have several companies represented here. I think those of you, please speak up, right? I think what I see is very, very strongly that all the vendors who are starting to understand, and some already have fully understand what it means to fill these kind of systems into a data center, and then things will happen over time, right? That we cannot see at this point. We had the same problem with GPUs, right? As we all remember, right? Let's remember fondly Titan and these kind of things, where over the years you start to realize that what we thought was safe is not longer safe, right? I'm sure these things will happen. But I'm not overly concerned at this point, and I hope, Laura, you agree with this, that if we fill a system, it probably will be quite okay should we put it in, I mean, within the parameters that the vendors give you, right?
Laura, if you want to respond, my question is unrelated.
Oh, okay. So I was just going to add on one other follow-up point. The whole idea, also bringing these systems in very early, was to see how, where they had variability, where they had sensitivity, the system itself that we needed to address, and what we could actually address in the environment, what we could change, and really what we couldn't change, and what the quantum system, keeping the quantum system true to itself, what can we change in the environment that we have it seated, and what can we not change? What physics and all do we have to honor? And I think one thing that's come out of this is, the software is, that really is going to have to take, a role in helping to fit the system within the environment. This is also why for like the Munich Quantum Software Stack, we have this telemetry environment too, that's really studying the space around the system itself, how it's reacting. Lucas had mentioned this about the trains, but also temperature variations, all of this sort of stuff. So I guess my rambling point is that these systems are unique and kind of the first time we've had this in these environments, and so we're going to have to use the software to compensate for some of this variability as we move forward, which makes it kind of interesting in a way, because we do telemetry and all in HPC. But I think the variance with the quantum is more, and that's going to lead to some pretty interesting dynamic responses to keep things stable and to keep it moving forward. So that the MQSS kind of has not just the HPC side, not just the quantum side, but it has like the environmental scope in all of this, and then how it adjusts, or how all that adjusts down to the actual operation once you get onto the qubits.
So I had a few kind of quick questions. The QDMI, in the QDMI case, it's implemented by the user. So it's just an API, right? And then the user goes and implements it. Do you guys provide any sort of common libraries or sort of, like, for example, if you need to do RPC transfer or whatever, like to transfer data back and forth, do you provide these libraries as part of the QDMI? So then there is the QDMI infrastructure itself has some common libraries and then plugins for the different users or the different modalities.
Yeah, so not really yet, I'd say. So this is definitely something that we need to get better at still. I don't know. I think we're doing quite well so far, but this is definitely a direction that I would like to see some improvement in, to actually provide people with more utility functions so that not everyone starts to build their implementation from scratch. I think this kind of generator that I've shown on this slide here is a first step in that direction, so that basically if you have static information that you do not need to worry about how to represent this now in C++ or something, you write your JSON file, you hit a generator, that is it. I think similar things, or at least the things that I have in mind, are for remote calls, some REST API calls, and providing better support for this. This is also on my rather short list, so I'd say over the next couple of weeks and months that we add more utility for that, to make it easier for people to actually implement these kind of devices. The latest release with the new template has gone a long way in that regard, that it's no longer just an implementation file with empty stubs and that is it, plus a little bit of CMake infrastructure, but it is the whole infrastructure. I think by now even including CI workflows for GitHub, so that you could test your things. It contains a test suite, and it has all of that set up. So I think we're progressing in that way, but there's still a lot of work to be done.
And the intent is to make QDMI independent from the rest of the MQSS software stack, right? So it can be sort of taken apart and plugged into a different software stack and still be used, right?
I would even go as far and say that's not the plan, that's the reality at the moment. Like it is a separate repository. It is standalone in a sense. Yes, it lives under the Munich Quantum Software Stack organization, and it has been created as part of this initiative, but the interface itself is not really tied to the Munich Quantum Software Stack or to the deployment at LRZ or to the deployment within the Munich Quantum Valley. It is really, this is supposed to be an interface. Call it a standard. I'm still not the biggest fan of the word standard, but at some point we need to talk about standards. It's at least, it is aiming to become a common interface for people to interface with quantum computers, independent of the Munich in there.
Fair enough. In one of the slides, you mentioned job, like you submit a job to, like, for example, in the QDMI, they have, like run job, cancel job, whatever, right? How is that related to the concept of job from a scheduler perspective? Right? Is it a one-to-one correlation, or are they two separate things here?
You could draw some parallels between the two, I'd say. I'd rather draw the parallel to the QDMI job interface basically implements what a typical quantum hardware provider gives you access to. Basically, exactly what's shown on the slide, this kind of cycle of things. You can submit a program there, you can specify some parameters like the number of shots, and you get back results. And in that sense, that kind of this asynchronous job submission, you submit something, you get back a handle that you can query for a status. I think this does align very well with your typical scheduler job, like in Slurm. So I think there is a match there. I've also seen, this has been demonstrated a couple of weeks back, so just at the end of the last year at the EQS3 meeting, that people have built a Slurm plugin. So similar, probably in the last meeting that you had in this round, QRMI was shown, and the integration with the Spank plugin and Slurm was shown. I think a similar thing can definitely be done with QDMI, maybe abusing the interface slightly. And some people over in Poland at PSNC have actually demonstrated this working prototype of basically integrating QDMI as a Spank plugin. So this can definitely work. If this is the way to go, I'm not too sure yet, but the current interface at least allows you to do that.
Right, and it also allows you, or like one of the, I think, requirements should be that Slurm can allocate one job, and then you can have multiple quantum tasks that run. So in my mind, a quantum task would be related to the QDMI job, and the Slurm job or whatever the resource management job contains multiple of those, right?
Yeah, I think it's just a matter of terminology. I think you mean the right thing, and the thing that is also that we aim to implement. I think what you want is you want to have a session. Basically, you want to have a session with the device. That's the resource allocation. That's, okay, I now have a handle that I can do something with the device. Then you submit multiple different jobs to the device, and then you free the session and basically give the resources back. I think that's the analogy that works here and that we're working towards.
So you talked about site APIs, and if you can go back to that slide quickly, the different, you categorize your different QDMI APIs, and one of them had the site API,
this one?
Interfaces. Maybe a few slides. Yeah, here, that one, right? So I have job, the query. So I have device properties, site properties, operational properties. In your experience, like for different modalities, could you find a common set of APIs among all those, all the different modalities, or do you end up implementing completely different things for the different modalities here?
Yeah, short answer, no, you can't really unify. Some things you can unify. So like something like a device name makes sense for every modality, obviously. Something like the number of qubits probably also makes sense for all modalities. Maybe feel free to disagree, but some things do make sense, some things definitely don't. The fact that a neutral atom system can load, move, and drop individual atoms, that notion doesn't make sense for a superconducting system where everything is fixed in space. So I showed this on the other slide with this extension, basically, where we implemented these different things where you can see a load, a move, and the store, and you can ask a site for an X coordinate and the Y coordinate. an X or a Y coordinate also doesn't make sense for a superconducting system. You could fabricate something, like you could imagine that there's still a location for a site for a qubit on a superconducting chip, but that information has little to no meaning. This is an aspect that we've discussed quite a lot about at the end of the last year, and that we're still reflecting on. What's the right way forward here? Is the right way forward to still have one interface and basically add enumeration values and properties to it from all different modalities and really make it a big interface where one particular modality then only needs, I don't know, 20% of all the enum values, and the other ones just simply do not make sense? Or is the better way forward to have multiple sub-interfaces or add-ons, or I don't know what the proper term is for that yet, basically feature add-ons that would say we have a common core, this is what everyone should provide, and then you have a neutral atom add-on. And a neutral atom device provider would exactly implement the core interface plus the neutral atom plugin. And the photonics person would implement the photonics additions, and so on and so forth, and to kind of have a more modular design of the interface. I'm leaning towards the latter to some degree because we've tried the first approach. This is basically what you see on the slide. And for one additional technology, that still works. For 5 different modalities, this will be quite a long list and will be hard to maintain. Right. That's just my feeling right now. I would expect that we do some work on this in the next couple of months and see more, but we'll definitely also try out the other way of doing add-ons to existing, basically, instruction set architectures.
Fair. Okay. To that, 2 questions left. Sorry. in your diagram with like the more detailed one where it shows the I guess quantum control node. Can't remember the exact term.
Yeah. This one here.
Yeah, this one. Yeah. You have the compiler infrastructure here. Is it then that classical compute, does it control all the different, like in the case of LRZ, for example, they have like 5 different quantum machines. Are they all under the control of this single classical compute, or is the intent to have one classical compute per per quantum computer that exists in the site?
So what's shown here is really the demonstrator that we did together with IQM. So this is a bit decoupled from the setup at LRZ. So this was really just aiming for a demonstration of how HPC-QC integration could look like with such an infrastructure. It's actually more so a demonstration of how QDMI actually ties into HPC-QC than about the MQSS itself. But I think this is still, it's still not quite clear to me what the best way forward here is. I think you need some kind of assignment of a classical resource for a particular maybe session, if we pick up that concept from before again. So maybe once you open a session with a device, you also allocate some classical resources with that session. So this is definitely not implemented yet, but this is my vision now, that you basically have the classical resources tied to that session. Within that session, you can do this whole variational loop and iteration, and after the session ends, also the classical compute goes away. So I think it does not make sense to have this as a rigid structure of, hey, here's a quantum computer, here's the classical resource to it, and they're so firmly attached to one another. I think this has to be more on-demand, stitched together or plugged together. But maybe I'm wrong. I'm just not 100% sure.
So perhaps I can add something to that real quick. I mean, no, I think I agree, Lucas. What you're saying is absolutely right. I mean, this has to be kind of a kind of an agile space, right? When you want to associate a resource with each other, which doesn't mean you potentially block it, right? So between allocating and associating with it and actually blocking it and making it exclusive is a difference still. So we're actually not looking into kind of tying it really tightly to a Slurm allocation that then blocks the quantum resource along with the Slurm part. But Slurm needs to weigh, or Slurm, whatever resource scheduler we want to use, we're looking at other ones too, has to know about that this may be needed. And then if you want to start gaining intelligent about it, adding estimators to it, adding kind of predictors to it when you need it at what time, so you can start interleaving with that. I think that's kind of where we're still working on getting the right strategies together. But having the association done, but at the same time being flexible of when the association is being used, if that kind of makes kind of sense, will be very helpful. And then back to the first question, yes, it has to be a center-wide thing, because we're going to have multiple compute clusters and multiple quantum computers, and we don't want them to really tie them together, tie them down to a particular installation. So there has to be kind of a global view that's independent of the slurm or job allocation for an individual cluster and the job and shot allocation for the individual quantum computer. There has to be a third part as a kind of mediator in between, which takes the global view, but also can do work with the individual allocations of the individual pieces. Did I answer the question? Does it make sense?
Yeah, makes sense to me. One last one. You talked about fault tolerant and the impact of that on the software stack. Do you have any sort of solid points that you can see fault tolerance actually impacting the design of what we're doing right now?
So it definitely affects. It affects all parts of the stack in some way or another. So first of all, it's not yet quite clear whether fault tolerance is something that happens within the stack or below the stack. So is it the devices that actually report, hey, I'm now a fault tolerant quantum computer. I have 5 logical qubits. My gate set is Clifford plus T, and my characteristics are X, Y, Z. Or is it that the device still reports, hey, I have 400 physical qubits. I have 10 different combinations of how you could build logical qubits out of that and which gate set that would amount to. Software stack, please figure it out how to use it. So that's an answer question to me, and where it definitely impacts the stack, because if the stack needs to figure this out, then yeah, this needs to happen somewhere. If the stack doesn't need to figure this out, then it needs to compile to a completely different gate set. And that gate set might be more similar across different modalities than we currently have. So the current gates, the native gate sets of all these different modalities are vastly different, from having global gates to just having discrete gates to, I don't know, having single and 2 qubit gates. Some have 3 qubit gates like neutral atoms, where some systems will have. There's so much variety in there that will probably not be there anymore when we reach fault tolerance, because the typical fault tolerance gate set is Clifford plus T. Yes, there are some variations to it, but that might actually make the stack a little bit simpler if we don't have to deal with that level. But that might really be far fault tolerance. So not like in 2 years or so, but maybe in 10 years or so, when we simply do not have to worry about that level of abstraction anymore. In the meantime, we will have to worry about it somehow. And I don't know who raised the point earlier about giving low-level access to the end user for playing around. But this is, again, something people in the fault tolerant error correction area domain should be able to experiment with new logical codes, with new protocols for, I don't know, state preparation, decoding. And the software stack should allow this. And some of those tasks, like state preparation, decoding, they are simply different tasks that we do not need to do for NISQ. That's one last point to touch all parts of the stack. The algorithms that you typically employ are also completely different. So the usage patterns are different. You wouldn't want to run a variational quantum algorithm on a fault tolerant quantum system. The point of variational quantum algorithms is that you do them on NISQ hardware, which only accepts shallow circuits and where you need the kind of iterative loop. You want to do something like Shor or Grover or phase estimation on a fault tolerant machine. So the kind of the usage path is also different, which might affect things like scheduling, prediction, estimation, resource allocation. So quite a few things change, I think. Sven, you had something to add there.
Yeah, I have something to add and share a dirty little secret. I'm actually one of those people in the world that have implemented several operating systems. And we have to remember that also on the classical side, everything that we feel is sort of done by hardware is not necessarily done by hardware, right? So a lot of the reliability aspects that we depend upon in our clusters and whatnot is actually done on the software level in the operating systems. Just that most of the time you don't see it because the operating system is busy doing error mitigation. And I would expect us to go about in similar mode for fault tolerance in quantum systems, right? It's just that then it's a matter of, is this below above the layer where the programmer sees it, right? In a classical system, it's not uncommon for, at least on some exotic systems, for the compiler to actually have to see the nitty-gritty details about how to ensure reliability in the system. And certainly the operating system sees it, right? So it's really a matter of layering and which APIs are exposed and to what actors.
Yeah,
and here,
I think sorry.
No, I just want to mention that, now we're talking about the software stack, but the software stack is something that is going to be seen differently from different consumers of the software stack. And right now, I think we expose this very openly to everyone. I'm talking in abstract terms because I'm not directly involved with the quantum software stack. Now we talk about this in very open terms, right? We can think now also about what's happening in GPU domain, where in principle, what's going on in the software stack is not secrets in the sense that we know roughly what's going on. It's just that we're never going to see the code, right? It's closed down, and some have some insights under NDA, but most of the time we don't see what's going on there. And over time, I do expect us to see some similar movement in the quantum domain. Sorry, Lucas, you're really the expert here, so I'll leave back to you here.
I fully agree with everything what you said. And the key thing is just we need to find the right APIs to expose to people so that things like Sven, you just mentioned, can actually happen. Like if we define the APIs right for these different levels, then the people that don't want to worry about these aspects, they don't need to. It's a very select few people that will probably have to deal with how to encode logical qubits on top of physical qubits. There will be people that need to do this because that's how you get a fault-tolerant quantum computer eventually. But hopefully it won't be the end users in the future that actually want to make use of the quantum computers. Hopefully for the end users, they have APIs that they can just submit a job and that job solves their problem faster than a classical computer. And we need all those APIs in between. And the sooner we start working on them and agreeing on them and learning what works and what doesn't work, the better.
Awesome. I think that was great. We went half an hour over time, but I found it very useful. Thank you, Lucas.
You're very welcome. Thanks for being here.
Thank you, everyone.
Thank you.
Thanks, everyone.
Bye-bye.
Take care.
Thank you.
Thank you. Bye-bye.